Hey guys, Professor Dustin here, and this video is going to be about banking. This is an application of uniform circular motion. So this is a great way to learn about uniform circular motion and centripetal acceleration, but it's also a great topic because this is how roadways are actually designed to make them safe. If you're interested in transportation systems, banking is actually a really important concept to understand. So the idea is that we have a car which is going around in a circle, or at least a small part of a circle. The circle has a radius r, the car is moving at a constant speed v, so it's constant speed v at a radius r, so therefore we're in uniform circular motion. We know what the acceleration of this car is because we've discussed it already. It has centripetal acceleration directed towards the center of the circle. I can draw that on towards the center of the circle, AC. And we also know what the magnitude of that acceleration is. Magnitude signs around it. It's v squared over r. Okay, great. So that's the acceleration of the car, but what we know from Newton's second law is that accelerations only happen because of the sum of forces. You add up some forces, divide by the mass, and you get the acceleration. So we should be able to say which forces are creating that acceleration towards the center of the circle. So what I'm going to do to try to answer this question is pretend I'm standing right here at the bank of the roadway looking behind the car as it's going around the circle. So I'm going to redraw the picture as if I'm right here looking behind the car. Okay, so from this perspective, I'm behind the car. It's traveling into the board away from me. I can also put the centripetal acceleration on. It's now towards the center of the circle like that, AC. Okay, so to answer which force is creating that acceleration, I should draw a free body diagram as a precursor to solving Newton's second law. So it's a massive car. I know there has to be a gravitational force acting on this car. I know it's directed downwards, right there. What other forces could be acting on the car? Well, I have a surface here. So the surface is acting on the car, pushing upwards. And of course, we know that that's balancing against the gravitational force, and that's called the normal force, Fn. Okay, so what other forces could be acting on the car? I can't think of any off the top of my head yet. So then I should say, okay, well, which of those forces is creating the acceleration towards the center of the circle? But neither of those forces can be causing the acceleration towards the center of the circle because neither of them are pointed towards the center of the circle. I'm obviously missing a force on this diagram. So I have to think a little harder about what forces could be here. So I have only three things in my universe: the Earth, the surface, and the car. I've got the interaction between the Earth and the car. That's Fg, so that's not going to help me. So the only interaction I can deal with is between the car and the surface. Okay, I already have the normal force. That's obviously the interaction between the car and the surface. But surfaces can act perpendicularly, but they can also act in a parallel manner through friction. So obviously there's some kind of friction between the surface and the car, which is causing this centripetal acceleration. That must be a frictional force. I'm going to draw it there. I'm going to call it FF. It's a frictional force, so I should be able to actually answer what kind of friction it is. Okay, the car is obviously moving, but it's moving in this way, into the board. It's not moving in the radial direction. So therefore, in the radial direction, there's no motion, and this friction force must be the static friction force. Okay, so this is my picture now, and I know now that the static friction force is what's holding my car onto the road. Actually, that makes a fair amount of sense, right? My car would be flying off the road. It wouldn't be able to stay on the road if my tires didn't have enough friction between the tires and the road. So it makes a lot of sense that the tires are what is keeping me from sliding off the road. But of course, this is now a dangerous situation in terms of safety. My acceleration is v squared over r. My acceleration is going to depend just on the static friction force. I can control my speed. I can drive as fast as I want. I can't control the static friction force. The static friction force has some maximum value given by the weight of the car and the coefficient of friction between the wheels and the road. If it's constructed in such a way so that the static friction force is very small, maybe I could drive fast enough to just fly off this road. That's dangerous because we don't always have direct control of the static friction force. Maybe it's icy, or maybe there's water on the road, and maybe it's too slick and unsafe. So the problem here can be alleviated by doing something called banking. So if we take this horizontal surface and bank it a little bit to make the road slanted, this road becomes safer. And so what I'm going to do now is I'm going to redraw this picture under the banking situation. Okay, so here's a road with some pretty modest banking. We call the banking angle theta. It's going to be right here. And I'm also going to put the centrifugal acceleration in. Again, based on this picture here, I know the centrifugal acceleration must be towards the center of the circle, like directed in that, like that. Okay, so now I want to play the same game. What force is creating that centrifugal acceleration? So I'm going to go with a free body diagram again. Starting with the gravity, we know it should be there, and it should be directed straight downwards. FG. Okay, what other forces can we have? Well, we know we have to have a normal force because there's a surface here. Normal force acts perpendicular to the surface. This surface is tilted, so my normal force needs to be tilted. I'm going to try to do that as best I can. Okay, so the normal force is now tilted at the same angle that the track is tilted at. Okay, so now I should say, do I have a force which could be causing the acceleration towards the center of the circle? In the flat case, the answer was no, because everything was vertical. But in this case, the gravitational force is vertical, but the normal force has both vertical and horizontal components. I'm going to draw those in. So it has a horizontal component straight up like that, and it has a vertical component to the side like that. If I pick a coordinate system like this, x, y, then I can call Fn x that component and Fn y that component. But now look at what I've done. I have Fn x in the radial direction, and that's the same direction as the centrifugal acceleration. I don't need friction to make my car continually move in a circle. All I need is the normal force. So in some sense, this is a lot safer because, okay, I might be able to drive fast enough to overcome the normal force, and of course there would actually be friction in this diagram in sort of the real life situation, but even without friction, if this thing was made of completely ice, if this was a completely icy road, there still is some range of speeds at which this is safe. So you're never going to make a road 100% safe, but you're going to be able to make a road safer because no matter what the situation is, there is some speed at which this road is going to be safe. So let me continue to solve this problem, this Newton's second law problem, to sort of show you the connection between the velocity and this angle. So I want to sum up the forces in the x and y direction to get a better handle on what's going on here. Some of the forces in the x direction, some of the forces in the y direction. So in the x direction, I have only one force in the x direction if it's Fnx. Now I should be able to write Fnx in terms of that normal force and in terms of an angle. So what I need to be able to do is figure out how to get this angle onto this picture somehow. And if you think about it a little bit, you should be able to figure out that that angle right there is the same as that angle.
I just want to give a few details on how I found that angle, because I know that's a complicated thing to do if you're not used to figuring it out. So the question is, why is that angle the same as that angle? So what I'm going to do is I'm going to add another line to this picture, a line which is parallel to the normal force right here, but which is related in some way to this triangle. And that's going to be right here. Okay, so that arrow is parallel to the normal force. This is a straight line, and this is parallel to this. Okay, so now it should be pretty clear that this angle and this angle are the same, because here we have a straight line which is being intersected by two parallel lines. So that's a geometric rule that for a straight line and two parallel lines, that angle is equal to that angle. So then we can use our knowledge of triangles to figure out that this angle right there is 90 minus theta. This angle right here is a 90-degree angle because I said this was parallel to this guy. And so this angle is going to be 90 minus theta, and that is theta. And that's a proof of why this angle is equal to that angle.
So if I do that, I can then write this Fnx is Fn sine theta. And of course what I should do now is I should write, that's my left-hand side of my Newton's second law, I should write on the right-hand side m times the acceleration. Well, I know the acceleration is v squared over r, so I could just write this as m v squared over r. Okay, so that's my Newton second law in the x direction. Now I'm going to do Newton second law in the y direction. In the y direction, I have Fny, but that's just going to be Fn cosine theta. And that's in the positive direction. In the negative y direction, I have Fg. I'm just going to write that as m times g. So I'm going to write minus mg. That's the left-hand side of my Newton's second law. The right-hand side, m times a, the acceleration in the y direction. But this car is not accelerating in the y direction. It's only accelerating in the x direction, so I get 0. So now from the y component, I can solve for the normal force. Just take mg, move it over, divide by the cosine theta. I get Fn is mg divided by cosine theta. And now that I have a solution for what the normal force is, I can take that normal force, plug it in right there in the x component. That looks like mg cosine theta times sine theta is equal to mv squared over r. So now I can start simplifying things down a little bit. I have an m in this term and an m in this term, so if I divide the whole thing by m, I just cancel out my m's. If you remember your trig identities, sine divided by cosine, that's a tangent. So I have a g times the tangent of theta is equal to v squared over r. And that's my final result. So if I want to make my roadway safe for some speed, so let's say I want to make a roadway that has a speed limit of 50 miles an hour, implying that going over 50 miles an hour, we can't guarantee you'll be safe, but if you stay under, no matter what the road conditions, you will be safe. Set this to be 50 miles an hour, set this to be whatever the curvature of your roadway is, which depends on the geography and what you're trying to accomplish. And this tells you exactly what the angle right here has to be in order to make your roadway safe, even ignoring friction. If you put friction on this road, obviously you could go faster because friction would hold you to the road. But you want to make it safe no matter what the conditions are, and this is how you do it. This is also done on racetracks, so you want to make the racetrack as safe as possible so the cars can go as fast as possible, so it's as exciting as possible, but it's based on the principle of keeping the car on the road no matter what the road conditions are. Okay, so this has been banking. I hope it's been helpful to improve your understanding of this sort of complicated topic a little bit. Thank you for watching. I'll see you guys next time.